Welcome. I am Professor J. N. Mandal, Department of Civil Engineering, Indian Institute of Technology, Bombay. So, I will now discuss the procedure of the test. First, the proving ring is attached to the cross head of the frame. Any other necessary extension pieces and the upper platen is fitted securely to the lower end of the ring. The dial gauge is secure and checked, ensuring that the end of its stem makes contact with adjustable stop on the ring. The lower platen is adjusted to provide the space to insert the specimen. The strain rate is set to 1.5 millimeter per minute on loading machine. The test specimen is prepared from the U100 or U38 tube. Measure the dimension of the specimen. It should have a diameter of 38 millimeter and length of 76 millimeter. If the length is 76 millimeter, then diameter will be half of the length, that means 38 millimeter. The specimen is set up, record the 0 reading and apply the compressive load. The readings are taken till the proving ring pointer move in opposite direction. Then unload the specimen. Catch mode of failure of the sample and remove the specimen. Remold and repeat the test for 2 more samples. Measure the water content and plot the graph and do the required calculation. I will now show you that how you can calculate the specimen calculation. So, this is the specimen calculation for unconfined compression test. So, we know that initial length of sample that is L is equal to 76 millimeter. And initial diameter of sample D is 38 millimeter. So, we can calculate that what should be the initial area, and that is designated at A0. So, A0 can be calculated at A0 is equal to pi by 4 into d square, or pi by 4 and d mean 38. So, 38 millimeter square. So, if you calculate, you can have the initial area A0 will be 1134.11, this is millimeter square. So, you can calculate that what will be the A0, that means initial area of the sample. Now, I will show that how to take the reading for unconfined compression test. So, first of all, you can measure the deformation, that is in millimeter, then calculate what will be the load in kg, then you calculate the load in kilonewton, then take the strain value, that is in percentage, this into 10 to the power minus 1, and then you can measure the corrected area, that called AC, this is millimeter square, and then you can calculate that what will be the axial stress, that is KPA. Okay. So, initially, that is all this is 0, 0, 0, 0, and corrected area may be 1134.11. This is initial area what I have shown you earlier by calculation, then actual state is 0. So, this is you can say as a serial number. Then second case, you are measuring the deformation of the sample. Let us say deformation is equal to 0.3 and load is equal to 3.9 kg, and the load in kilonewton will be 0.038. Then strain is 3.9 and corrected area you can have 1138.55 and the axial stress is equal to 33.37. So, you have to continue like this different, that deformation, it may be the 0.6, it may be the 0.9, or it may be 1.2, okay, 1.5, like this you can continue, okay, and you can take the reading and can continue this. Under different deformation, you will have the load in kilonewton, strain and the corrected reading. I am just showing you one of the calculation here for this step, serial number 2. So, here load, that is if you convert in kilonewton, that means load in kg, this into 9.81 into 10 to the power minus 3. So, load will be is equal to what is load? Load is 3.9. So, 3.9 into 9.81 into 10 to the power minus 3. So, if you can calculate, this is in kilonewton, will be 0.038. So, this is 0.038 is kilonewton. So, you are having 0.038 kilonewton. That means load is 0.038 kilonewton. Now, we measure the strain value. Okay. Strain, that is in percentage. This is equal to deformation of the sample. Deformation of sample into 100. Deformation of the sample divided by length of the sample. Okay, into 100. Yeah. So, strain is equal to deformation of the sample divided by length of the sample into 100. So, if you now calculate, then deformation of the sample, you know, that is 0.3. So, this is 0.3. This divided by what will be the length of the sample. Length of the sample I told you earlier, that is length of the sample is here, that is 76 millimeter. So, this divided by 76, this into 100, this is equal to 0.39. So, this is 0.39 is the strain value, 0.39 is the strain value. So, here strain value 10 to the power minus 1. So, this 0.39 will be the 3.9. So, you calculate the what should be the strain. Now, we have to determine that what will be the axial stress, because this corrected this area already we have initial value we have calculated 1138.55. So, we have to calculate what should be the corrected area and what should be the axial stress. So, this corrected area we can calculate. This is corrected area. Corrected area is designated at AC. AC is equal to A0 divided by 1 minus EL. So, what is A0? A0 we have calculated earlier. That means A0 is 1134.11. Okay, this is A0. So, A0 is 1134.11. This divided by 1 minus EL. That means EL will be equal to your this value. Okay, that means it will be the 0.0039, 1 minus 0.0039. Okay, that is the strain, 1 minus epsilon strain. Okay. So, if you calculate this, then corrected area will be equal to 1138 0.55, this is millimeter square. So, which we have shown you here that what should be the corrected area. So, this is the corrected area 1138.55, this is corrected area. So, now we will calculate the axial stress. So, axial stress is equal to load divided by corrected area. Corrected area. So, load is equal to this, load is 0.038 kilonewton. So, this is 0.038, this divided by corrected area we calculated here 1138.55, this into 10 to the power minus 6. So, because we are expressing in terms of kilopascal, so this axial stress will be equal to 33.37 kilopascal. So, you are having the axial stress value in from here table 33.37. Like that, for all other deformation also you can calculate that what should be the axial stress. So, you can calculate that axial stress, you can calculate that what will be the axial stress, what will be the corrected area, and what is the deformation. Now, based on this table result, you can draw a correlation between the axial strain and the axial stress. I am just showing here. This is the axial strain. This is, let us say, this is axial strain in percentage. This is 10 to the power minus 1. And this is the axial stress. This is axial stress, that is Kpa. So, for the defined value of the axial strain and the corresponding axial stress, which you can obtain from this table, and then you can draw a curve. You can draw one stress strain curve. So, and you can also achieve that what will be the maximum value of the axial stress. So, here maximum axial stress is 100 kilopascal. So, from this test, okay, you can draw that what will be the stress strain relationship of the soil. So, from the stress strain relationship of the soil, you can determine what will be the maximum axial stress. In this case, we are having the maximum axial stress about 102 kilopascal. Well, you can also draw the Mohr circle and the failure envelope for unconfined compressive strength. So, you know that the sample fell, and that sample fell is about that axial stress value which I showed you here, that is about 102 kilopascal. So, you can draw in the Mohr circle diagram also. So, if you draw in the Mohr circle here, so this is sigma 3 is equal to the 0, this is sigma 3 is equal to 0, and this is sigma 1 f, which you can say that failure at the 102 102 kilopascal. So, this is sigma 1 F, this point is sigma 1 F, this point is sigma 3. So, you can draw a semicircle, and this is the failure envelope, this is failure envelope, this line is the failure envelope. So, this is the normal stress versus shear stress. So, you can determine what should be the shear stress, that is tau F is equal to CUC. CUC is equal to maximum shear strength. So, unconfined compressive strength value, that is QU, or you can say that sigma 1 F, that is 102 kilopascal. So, maximum shear strength, that is CUCC, CUC will be equal to sigma 1 F divided by 2. So, that means 102 kilopascal, this divided by 2. So, this will give about 51 kilopascal. So, you can determine what will be the maximum shear strength using also this Mohr circle diagram. From here you can also calculate. So, I will show you next is the triaxial shear test. How we can determine the shear strength parameter using the triaxial shear test. So, triaxial shear test is very important in soil mechanics. It is most important and somewhat complicated test. So, it simulates the field condition most among the other tests for determining the shear parameters, that is cohesion and the angle of friction. So, these triaxial shear tests have the 3 possible drainage path before and during the shearing. So, one is called unconsolidated undent test, it called also consolidated undent test, that is designated as CU. It also that other type of test which you call that consolidated drain test, and that is called the CD test. So, I already earlier explained when it would be the unconsolidated undent test, when it should be the consolidated undent test, and when it should be the consolidated drain test, depending upon that whether there is a drainage or there is no drainage, whether it is consolidated or whether it is unconsolidated. Now, here we have shown the triaxial setup, and you can see this is the sample of triaxial sample, that is 76 length and the diameter is half, that is 36. Here is a proving ring, you can measure. So, these are the total setup of the triaxial set. You can measure here also the pore water pressure through here. So, this is that triaxial test apparatus for the determination of the shear strength of the soil, and particularly that what is cohesion and the angle of shearing resistance. So, this apparatus and that what will be the accessory required for the triaxial test. So, apparatus or accessory required triaxial shear load frame with 30 different rate of loading speed. Triaxial shear pressure cell, that is triaxial cell consists of, it may be cylindrical perfect cell with a ram loading arrangement and 4 Klinger valve connection at the base, proving ring and dial gauge for recording the stress and the deformation. if an electronic digital recording system is available, it should include a load cell, that is called LVDT, that is linear variable displacement transducer, and the pore pressure transducer. So, next is the lateral pressure assembly. Volume change burette with the proper attachment, static molding device for remolding the triaxial shear specimen. Now, these are the accessories are required to perform the test. Now, what are the procedure? First, feed the top cell properly, taking care to fit the loading ramp on the top of the sample pad. Then allow water into the cell at the required pressure. Initial reading of the strain and stress dial are taken. The loading is set at 1.25 millimeter per minute and loading commenced. So, you have to remember that loading rate is important. So, here you are keeping the loading rate at 1.25 millimeter per minute. Reading of stress and the strain dial are taken at a regular interval until the sample fill. Now, type of triaxial shear test. As I said, it may be unconsolidated, undent triaxial test. In this type of test, the sample specimen are tested with 3 or 4 different lateral pressure without allowing the volume change in the sample, either when the lateral pressure is applied or during shearing. Second, the volume change and the pore pressure valve are closed throughout the test. Next, perfect undent condition for a saturated condition gives predominantly the Cu value, that is known as apparent cohesion, while the pi angle of shearing resistance will be the 0. Now, you can draw for the unconsolidated undent test, you can draw this is the shear stress and this is the normal stress. You can have this number of the Mohr circle where pi is equal to 0 and this is the failure envelope. You can have only that Cu value. That means what is apparent cohesion intercept for the unconsolidated undent test. So, for the unconsolidated undent test, you can determine what will be the apparent cohesion, that is Cu, where pi is equal to 0. Now, next is that consolidated undent triaxial test. So, soil specimen is consolidated under a given lateral pressure for sufficient time and corresponding volume change is recorded and excess pore water pressure dissipate in this process. Testing commencement by closing the drainage valve, so that the undrained condition is maintained during testing. So, this is the case in case of the consolidated undrained triaxial test. Thank you.